Hello everyone, I am Sohamchari and I am here to present our work Android Malware Detection based on static analysis and data mining techniques, a systematic literature review. The co-authors of this paper are Hemant Rathore, Nishant Verma, Sanjay Sahai and Mohit Seva. First of all, I would like to thank EAI Broadnets 2022 for accepting this paper and allowing me to present in the conference. So we will start off with the introduction and some basic malware evaluation and taxonomy. Then we will discuss current malware detection engines and slowly transition to data mining based malware detection framework. Then we will discuss previous studies in malware detection using machine learning and deep learning. And finally, we'll also discuss some open issues and challenges in this field. So let's start with malware, right? So the term malware is basically derived from malicious software. It is a software program that is designed with an malicious intent. Right? So malicious intent could be anything such as stealing end user information, deleting or corrupting user files, or observing behavior or spying on the user without the consent of the user, and so on. So this malware usually comes in various forms such as virus, worm, Trojan, spyware, ransomware, bots, etc. So why do we need to tackle these attacks, right? So as per Statista report in 2022, we can see that from 2015 to mid 2022, there have been around 58.9 million malware attacks worldwide. So, and according to Forbes, it is expected that cybercrime will cost around $10.5 trillion annually by 2025, right? Which is a huge cost of the global economy. So we need to be ready with our detection frameworks to tackle these malware attacks. Now, since our study is focused on Android malware, I'll like to highlight a few points here. So Android is currently the most popular mobile operating system with 71.8% market share. It has seen a rapid growth in user base, but this growth has also compromised Android security to some extent, right? Such as so we can see here these plots are from AV test 2023. So we can see from 2008 to 2020 there has been a rapid growth in malwares and PUAs, potentially unwanted applications. And talking specifically about Android, we can see that there also has been a rapid development of Android malware, specifically in 2016, 17, 18, and so on. So, our study focuses on Android malware detection. Right? So we usually have different types of malware. The first one is static malware or the first generation malware. So when we develop new malware from scratch, it is basically a first generation malware which has a fixed malware structure. So examples of these are virus, Trojan, worms, etc. And then we move on to the second generation malware, which consists of encrypted, polymorphic, and metamorphic malware. Right? So in encrypted malware, we try to encrypt the malware program itself, so that the signature of the encrypted malware does not match the signature of the original malware, and so this can easily bypass the signature based approaches. The second one is polymorphic malware, where malware constantly changes its identifiable features using a mutation engine. So this makes it very difficult to detect these types of malware. It uses various obfuscation techniques to achieve so, such as uh, renaming variables or methods in the source code, packing the code, or insertion of dummy code, and so on. Then we have metamorphic malware, which basically replicates malware into a new malicious code which almost has no resemblance to the previous old malware, right? And in this case, we also mutate the mutation engine, which makes it even more harder to detect this type of malware. So now we will discuss the various detection engines that have been developed over years. So traditionally we have the signature based detection and heuristic based detection. Right? So each software program has a digital footprint which we call a signature, and signature based detections basically store the signatures of known malware in a database and try to match this with the signature of a given sample, right? If it matches the one of the samples from a database, then we can classify it as malware. Similarly, in heuristic based detection, it is a proactive approach where the domain experts design and develop various rules or patterns that identify this malware. So in this figure we can see a traditional detection system where we have a client end and where we have server end, right? So client end is basically deployed on user and smartphones or laptops and so on, and in server end is basically deployed on antivirus industry infrastructure, right? So we have various crawlers, web crawlers deployed by these antivirus industries that traverse throughout the internet and try to collect new potential malware samples. Then The domain experts analyze these samples, and if they find it to be malicious, they generate signatures and heuristic to detect them. They update their own database with these new malware heuristic and signatures, and then they send these heuristics and signatures through a antivirus update to the client end, where the same is being done at the client side as well. And finally the anti-malware engine basically does the signature and heuristic matching using this database. So this is the traditional detection system which uses signature based and heuristic based detection. But modern malware can now easily bypass this signature based detection with various obfuscation techniques, as I already mentioned, and even small code changes can easily bypass these methods. So then we have cloud-based detection, which is basically a two-layer approach with client machine and a server machine. So initially client machine analyzes the signature of the sample. If it is found as malware, it is labeled as malware. Otherwise, it is sent to the server machine. Now, server machine is equipped with various detection engines, and they use the voting methods to classify a sample as malicious or not. Although reliable, this method is computationally expensive and requires very high-speed connectivity. So then we move on to the data mining based detection, right, which uses various machine learning algorithms. So this is also a two-step process. We have feature extraction, where we extract features from the applications, and then we have the classification and clustering, where we use various algorithms to develop detection frameworks or detection models on these extracted features, right. So the literature has suggested that data mining based approaches have found and proven to be useful for Android malware detection, right. So we'll discuss the framework of the data mining based detection. It usually has 5 steps. The first one is data collection, where we collect various malicious and benign applications from various sources, right, such as app stores. Then we have the feature extraction phase, where we analyze these applications and extract identifiable data patterns or features that might be useful for us in identifying malware. Now we usually end up with a lot of features, many number of features, which some of them might not be very relevant. So we try to select subset of features that will be the most relevant among them, right? Then we use the learning algorithms, various machine learning algorithms or deep learning algorithms on these selected features, and then we use these models to detect whether any given sample is benign or a malicious sample. Now we'll talk about these phases in detail. The first one is data collection phase. Now, as I said, right, the malware detection is highly dependent on the data we train it on, right, and so the data quality is extremely crucial. So for this application, we have malware and benign apps basically obtained from various app stores, like such as Google Play Store, APK Mirror, APK Pure, F-Droid, etc. So researchers have obtained applications from various other sources as well, such as VX7 by Santosh et al., Playdrone and Android Malware Genome Project by Gao et al. There have also been authors who have collected malicious applications and shared with the research community, such as Drebin, a benchmark dataset by Arp et al., Android Malware dataset by Argus Lab, and so on, right? Now we need to extract the data patterns of features from these applications so that we can detect using our classification models. So this can be done in 3 ways again: static analysis, dynamic analysis, and hybrid analysis. So in static analysis, we try to extract the features without executing the application. So some examples of these are permissions used by Rathore et al., intents, opcodes, etc. Then we have dynamic analysis, where we, in the control environment, we try to execute the application and extract features. So this involves system calls, API calls used in Fan et al. In 2015, etc. And finally, we have hybrid analysis, where we try to combine static and dynamic analysis, and it tries to balance between the advantages and disadvantages of both of the static and dynamic analysis. Now, static analysis usually achieves a better code coverage, overall code coverage, and literature has suggested that it has been found to be effective and useful for malware detection, such as a study by Penn et al. In 2020, right? So various static features include permissions, Android permissions, intents, opcodes, components, etc. So here we show a distribution of these features for malware detection used in previous studies, right? So you can see 33.3% of the studies have used permission as a feature. Then 27.3% of the studies have used API calls as a feature, and so on, right? So these are the various features that have been used in previous research. Sorry, yeah. Then we have feature representation. Now after we extract these features, we need to represent in certain formats or certain forms that our model can understand, right? So we can have vectorized representation, where we represent these features as a vectors using techniques such as one-hot encoding or TF, IDF, word embeddings, etc. So Abhilash et al. Have used doc2vec technique and achieved 95.3% detection accuracy. Similarly, Karbab et al. Have used one-hot encoding and achieved 99.84% accuracy. We can also have tree-based representation, where we try to analyze the source code of the application and generate an abstract or create an abstract syntax tree of the application, which is then used further for classification or clustering. Yeah? So Tan et al. From 2015 is an example where they have used tree-based representation and achieved 95.9% detection accuracy. Finally, we have graph-based representation, where we represent Android apps as specific graphs such as control flow graphs, CFGs or IDFGs, interactive data flow graphs. So Jerome et al. And Gao et al. Are some of the studies that have used CFGs and achieved a 0.89 F measure score or 87.85% accuracy. So the vectorized representation is the most widely used representation in the research community for Android malware detection. Now, once we get the data, we need to preprocess it. We need to make sure that we remove inconsistencies and handle all inconsistencies as well. So various steps are data cleaning, where we handle this inconsistency, missing values, and so on. Usually we collect applications from various sources, right? So we need to combine them into one, where we merge data from various sources. This is called data integration. We also have data reduction phase, where we remove irrelevant data. And finally, we have data transformation phase, where we perform techniques such as normalization. We try to normalize data within a specific range, data aggregation, and so on. So one of the studies, Masarelli et al. From 2017 have calculated DFA coefficients for each of the features as one of the data transformation steps. Now, this data preprocessing and extraction usually gives us a lot of features which may lead to curse of dimensionality. So we need to select the most relevant features among the subset of the features, right? So this can be done in feature ranking or subset determination. In feature ranking, we rank features based on its behavior and importance, right? The literature has suggested rough set theory or fuzzy rough sets such as Jansen et al. And so on. And in subset determination, we try to identify a subset of features that are the most significant ones, right? So this algorithm can be done in various ways. The filter one is where we rank features based on a specific source core. Then we have wrapper based techniques, where we select a subset when we try to generate the predictions, and then we check the performance of the predictions using this subset, which is basically an expensive method. And finally, we have an embedded technique, which is inbuilt with a learning algorithm, and it tries to adjust its weights based on the subset selected. So it captures the dependencies in a better way. Although it is essential to note here that some of these techniques might also be might also lead to overfitting. So Tam et al. In 2015 have used ensemble feature selection as one of the techniques. Now we move on to the learning techniques. We also have supervised learning, unsupervised learning, or semi-supervised learning. So in supervised learning, we have a labeled data set, where we use this data set to predict either a continuous variable, which is a regression task, or a discrete variable, which is a classification task. So some of the literature here is Liu et al., who have used J48 decision trees and achieved 98.4% accuracy. Similarly, other studies which have used decision trees and naive-Bayes algorithms. Then you have unsupervised learning methods, where we have unlabeled data, right? So we need to group them using clustering. So research again suggested K-means and PCA to be performing better, and a study TF Droid has also suggested that clustering approach performed better than non-clustering approaches, right? So finally, we have semi-supervised learning, where we try to combine supervised and unsupervised learning, right? So for example, Santos et al. In 2011 is one of the studies that have used LLCG algorithm, which is found to be performing better by mixing supervised and unsupervised learning. Now, after we build the models, we need to evaluate the performance, right? So we have various performance metrics. Again, for supervised learning methods, we have accuracy, error rate, precision recall, F score, AUC. Like most of us are already familiar with various of these metrics. Then we have unsupervised learning metrics, which includes internal and external metrics. So internal metrics includes various metrics such as rand index, sellout coefficient used by Rathore et al. In 2020, Kalinski-Harabash index used by Rathore et al. In 2020, and so on. And we also have external metrics where we observe the system improvement with and without the unsupervised learning techniques, right? And finally, we have also other metrics such as physical distance, like Euclidean distance, Manhattan distance, and so on. Logical distances like Pearson correlation coefficient and heat maps. So Rathore et al. Have used heat maps uh, to evaluate the model performance. We also have correlation metrics such as chi-square, Fisher score, and so on. Now I will try to summarize various studies that have used machine learning for malware detection. So initially in 2012, we can see a good detection rate using SVM model, extensive study of Android permissions, but a very highly unbalanced dataset, right? We can see only 121 malicious samples and over 100,000 benign samples. Further in 2016, we can see a good performance using a good datasets, but poor performance, with better feature reduction techniques and selection techniques as well. In 2018 also we can see a good performance model with decision trees with both static and dynamic analysis, but still a smaller data set, right? Then in 2019 we have some studies that have used clustering approaches such as k-means, uh, uh, bag of words features, but also faced cost of dimensionality uses due to a lot of features. In 2020 we have Rathore et al. Studies that have used random forest and achieve good performance for have performed exhaustive feature selection as well. And in 2022 we also have a study achieving a very good high performance, but a very small data set as well. Now let's move on to malware detection studies using deep learning. So initially in 2014 we can see a small data set, but using permissions, restricted boards model machine and deep belief network achieving a high performance of 96.5%. In 2018 we have several studies that have used a larger data sets and achieved good performance using convolution neural networks and deep neural networks. In 2019 also we have a feature graph representation using convolution neural network. They have achieved 94.3% F1 score. Similarly, we have studies that have used permissions, intents, convolution neural networks, recurrent neural networks, right? So we can see 2019 studies which have used BERT transformers and LSTMs and achieved good performance. Similarly, in 2022 now we have API call graphs as representation with a good balanced data set, convolution neural networks, and good performance of 91.27%. Right. So now we have discussed several studies in machine learning and deep learning domain, but there are still various open issues and challenges in this domain that need to be addressed and can provide prospects for future research. So the first point here is the lack of representative data sets. Now we usually collect applications from various sources, right? So this leads to unbalanced data set with very less number of samples from malicious class. So to sort this out, we had Zhou et al. And Arp et al. Giving the Malgenome project and Trebin to provide a collection of these malicious applications. However, we still require an up-to-date representative data sets to also acknowledge the recent samples in malware domain, right? Then we have incremental learning. So our models must be effective against representative known samples as well as recent samples, right? So we should be able to dynamically update our training sets to include the novel malware samples as well, so that our models are effective against all samples in general. So this have been again very less used in Android malware detection research. Then we have active learning, where we all know, right, the cost of acquiring labeled samples or labeling the data itself is a very expensive task. So we need to prioritize data to reduce the cost of acquiring labeled samples. So one of the studies, Moscovich et al. Have shown the efficiency in acquisition and improvement in classifier by using active learning. Then we have adversarial learning, where now since researchers have used machine learning algorithms to detect malware, malware attackers have performed simple perturbations in training or testing data, and they try to fool the malware machine learning models as well. So, but several frameworks have also been suggested to reduce the impact of these samples, such as Sevak et al. In 2020, 21, and 2022. Finally, we have explainability. Like most of the detection frameworks are able to detect malware, but they are not able to justify why any sample was detected as a malware or not. So this explainability helps us in understanding the malware behavior in general, right? So we could build more robust frameworks by understanding the behavior. So it is essential for us to know the explainability of these models as well. Concluding with the session, I would like to say, like, data mining approaches have been found to be significant in malware detection. So we studied the evolution growth of Android malware and detection strategies. We performed a very thorough survey of this framework and analyzed various studies. We provided highlighted or provided critical observations and insights for future researchers. And finally, we also discussed some open issues and challenges in this field, which need to be coped up in the further research. Thank you, everyone.